Hello, Water Managers. I am Alex Davis. I am with the Water Management Systems Division out at the Hydraulic Engineering Center. In this video, I'm going to cover real-time hydraulic modeling forecasting tools that we have available. The main objectives of this lesson is to learn about what forecasting options are available in the CAVI for hydraulic modeling, i.e. using HEC-HMS. Then we will discuss how to effectively calibrate an HMS model. Here's an overview of everything that we're going to cover. This will be separated into multiple more bite-sized videos. So in this one, we'll hit on the modeling calibration, the importance of observed data and performance metrics. In this section, we'll cover the HMS simulation framework, how it can be related to our forecasting, the importance of computation points and how we can utilize them to be more efficient at calibration, time series and spatial results so we can see how to view our results, and then when is the model calibrated? What's good enough for us to move forward? And then later on, we'll talk about forecast-specific editors. So we'll get into zone configurations and zones, when to use them, how to break them apart, and then we'll talk about the zonal and elemental overrides for the calibration, and then we'll look at the initial base flow reservoir and blending interfaces. And we will end this section with the HMS CAVI integration. So let's get started with some HMS calibration. So first off, we have to know what we're using for this HMS model. So with the forecast alternative, we're going to require the basin model, MET model, and time window and interval. And you can see all of this on the right image. And so most of the date times are all with the asterisks on the over here. And then we need the basin model, the MET model, and the time interval. You'll notice there's other stuff on here too that aren't necessarily required to be changed, but it's just nice to know about, such as the output. So by default, we're going to have an output of all. This is going to give us a lot of information saving to the DSS files. We might not want this. We might want to save a little bit of time and just let HMS give us what it seems to be the critical information. So we can change this all value to a minimal value in the dropdown. This will save to the DSS file any updates just to what's been deemed as needed for this. We can equally do something in between this all and minimal, and it's a selected option. So when we choose selected, this cogwheel over here will illuminate, and it'll open an interface where we can just kind of do checkboxes throughout. It'll gray out what's deemed minimal, so we can't unselect the minimal, but then we can add selected data sets that we want. So in doing this, it's going to save a little bit on the compute time for saving the records, and then a little bit on the disk space, but this can add up over time if you want to take the time to do it on your initial. Equally, we have these configurations down here, the loss rate, transform, base flow, routing, and snow configuration options. These all have to do with our zone configurations that we'll talk about later. And then we have our spatial results and spatial interval. These we'll do a little bit later in this video. Just go to how we can view data. And then the forecast alternative can be seen very similar to the simulation alternative in HMS. So down here we just have a graphic of results from an HMS model, and anything before this forecast time, it's basically the same as doing a simulation run in HMS. So we have our observed data going through the entire time span, and then we have HMS computing data. So the observed data is the black, the computed is the blue line. And then it starts differentiating over here at this forecast time. So this is when we let HMS just compute results, and we don't have anything to go up against it. So that's what we're utilizing when we do this forecast alternative. We're basing future response in our model and based on our calibration of what we have available to us. So let's talk about computational points. These are a very powerful and important feature that can make our life a lot easier. A lot of times these nodes are where we have observed flow data. But any element can be selected as a computational point. So you could have basins as computational points. You can have inlets, outlets, sources, sinks, anything that you want to. But most commonly it is going to be a junction. This allows us to do compute to points on our computation points. This becomes helpful whenever we're trying to do our calibration and we're only interested in a small portion of the model at a time, and we can compute just in our area that we're interested in as we proceed through the calibration process. And so this will save us on time for not having to run the entire model. And then once we select an element as a computation point, it gets shown a little bit differently. So in this graphic in the right, we can actually see that we have three calibration computation points. So we have one here, here, and here. They all have that red backdrop on it to let us know, like, hey, here is a computation point. If we right-click on it, we have an option to compute to point. And again, these are usually corresponding to observed data ones. That's usually what we're going to, the nodes that we're going to be interacting with the most anyway. So it's just a nice little visual indicator of like, oh, this is where we're at. Likewise, we don't have to do it just through this HMS interface. We can do it through this dialog down here that we'll talk about later. But down here in the bottom left, we have this little compute, and then the CP stands for computational point. And so this location is a computational point in our model, so we can do the drop down, do whatever computational point we're interested in, and hit the little button there to run the model to the computational point, just like we would if we were to right click and do compute to point. And so being able to subdivide our model by these computational points is part of the process and how we're going to take advantage of HMS with calibrating our model. So now that we have computational points and understand that they can be powerful for calibration, what is the actual process for calibrating these models? So first off, we need to get our boundary conditions. Our boundary conditions are generally going to be computed from HEC Met view, and from that we can get our precipitation grids, and then if we need it, we can get our temperature grids from Met view as well. And then once we have our boundary conditions for our model, we can run the forecast alternative to see what our starting point is. It could give you like spot on, like you could have your model fully calibrated out of the get-go, or at the very least, it gives you a starting point to see like, what are we doing? How far off are we? And what do we need to do to change our model? And so the first thing that we're going to do is we're going to start modifying our base flow values in our model. And for this, we're going to try to match our observed flow and our computed flow in that very first time step to try to make sure that these both get on the same level as each other. And then once we get that done through either the base flow editors or reservoir editors, then we'll calibrate using the loss parameters. And in this, we're going to try to get our timing and the intensity for our results in line. And then we might need to go back to base flow, change some of the other parameters that weren't the initial ones to try to get the tells and stuff like that for it. And through this whole process, we're hitting compute after we do each change to see how it impacts it and trying to get various parameters in line as much as we can. And so even though we've gone through and made some points, now we might have to go back and change the initial base flow. So it's a pretty repetitive process through this. And it might just take several iterations to get through. Then we move to the next point downstream. And so this is a process where we're starting upstream, the most upstream place, so the headwaters. And we're just going to progress our way downstream since the headwaters impacts the items downstream. And so with knowing that there's this impact, we have this potential to use blending. Blending is an option that more or less replaces the computed model results with your observed data, because you're most likely not going to get your observed data and your model to be identical to each other. Um, so they're going to be a little bit off. And so if you don't want to have that error going downstream, you can turn on blending to overcome this. Um, and then you can do your calibration at your next uh, uh, computational point. When you do this, just make sure to uncheck your blending whenever you're done with it um, as we go through this process. Okay. And then again, this will take advantage of the compute to point options as we progress. And then also I wanted to point out this program setting. So in the program settings under compute, we have this compute all elements if unchanged. So this comes into play if, let's say we just have our rivers branching and we have observed data for one branch really close to where they merge together, but then the other one doesn't. And so to calibrate the one that doesn't have it, we have to use a location downstream after the two have merged. But like we already have this one branch, it's calibrated based on some observed data really close to where they merge. So we're not changing that. We're focusing all on this other branch that we need to calibrate at this time. And so we can uncheck this compute all components if unchanged. And so that means that one that's calibrated, HMS isn't going to keep on computing what's going to happen up there, can get the same answer every time. It's just going to push that result down to where it's needed and where it actually impacts the model being changed. So this is another option to make sure it's not checked in this case, to just save a little bit of time since we're going through this tedious calibration process, because we're not going to be running the model just like once or twice. You might be running it like 10, 20 times, who knows? And so you don't want it computing the entire model every time you do this. It's just going to slow down the process and it's not going to make any changes to the answer. So this is a good one to have unchecked for this process. Okay, so now that we know how to calibrate, how do we know when the model results are good enough? So here is what we use a lot at HEC at the bottom graphic. So this is, you'll find this on like the HMS documentation pages and various other places. And these are two works by Morcelli and others. So the RSR has the 2007 next to it. So that's a 2007 publication titled Model Evaluation Guidelines for Systematic Quantification of Accuracy in Watershed Simulations. And then the other three statistical values we use for gauging if we believe it's a good, very good, satisfactory, unsatisfactory, also comes from Morcelli and others, but it's a 2015 publication under the titled work of Hydraulic and Water Quality Models, Performance Measures, and Evaluation Criteria. So this is what we use for our statistical boundaries for what we consider is very good, good, satisfactory, and unsatisfactory. And to some degree, you can look at the graphics at the top to be like, hey, this one on the left, it's not doing too hot. We're missing um, the first little peak that's a little bit under 1,000 altogether, and then we're not getting close to the intensity of the main peak. So we know it's not good. And then we can calibrate it and we can get like, oh, this is looking good. But then we'll use the statistics down here to figure out like, is it good enough? It probably is, but now we can have some sort of backing behind published works to be like, hey, this is good results. We don't need to proceed. Um, these statistics are just what we use, and other offices, other places might not use these same values. Um, I know I've mentioned to people before, like, hey, I'm just looking for an SC of 0.7, and they laughed at me because like that wasn't good enough for them. That wasn't good enough for their office. So it's a matter of at what point do you offset this time it takes to do this calibration with the modeled results being different. Um, and so this is just what we use to figure out if we believe the model is doing good enough, which is always a hard question. And so now we know what we deem as good enough. But how do we actually see these metrics and results? Um, and we need these models to be reliable to predict the runoff from the look back period to have useful results in the forecast. And so all these metrics are just looking at the time before the forecast time. That's where we have our observed data, and that's where we can actually make these. And so if we have that period where we before the forecast time is being good, then we have a higher confidence in our results after the forecast time. If we don't have good results, if we don't have models that we feel confident in before the forecast time, then we're not going to have results that we're confident in as being accurate. So here are the four main ways that I would look at data, the results, in HMS or in the CAVI from the HMS results. So we'll just go left to right. The left one is a graph at a single junction or node. Um, Here we can see graphically how the observed data and the model data compare to one another, with the blue line being what HMS is saying um, is happening, while the black line is what we know is happening through observed data. So we can go through and look, and this is what is probably going to be one of the main things when you go through your calibration through your computation points. And then the second one, the summary results down here, it takes basically what we see in that visual, and now we're changing it into numbers. So now we can see when our start and end time were and various things that we're using, but then we can see the computed results. The computed results are what's coming from HMS, and so we can just kind of see like what's happening. But then what we're interested in is how that compares to the observed flow underneath of it. So in this case, we can see our peak discharge and date at which the peak discharge is happening in our reserve. It's doing the same time and intensity as the model's predicting. But then we can see our volume through the what's happening is a little bit different. But then down here we have some statistics that we just went through, and with a Nash-Duff cliff of 0.925, that's well into the very good range. And so we can see that we're doing pretty well overall, even though our volume is a little bit off. So those first two are looking at a single point, single point of interest. And now the next two are going to be looking at the system more as a whole. And so this third option is the spatial results. So earlier on we were talking about what needed to be done for the forecast, like what it wanted for a forecast alternative. This was the spatial results option. So this one's just showing the Nash-Duff cliff, so it doesn't really need the time interval. But just turning on the spatial results allows us to see Nash-Duff cliff in this way. And so from this view, we can see a quick at system glance that a good amount of our model is doing pretty well. So the legend is down there in the bottom right, and so this is following that more Sally option with the green being very good, the lighter green being good, the orangish color being satisfactory, and then the red is unsatisfactory. And this is all customizable. We understand that not everybody's going to use the same values as us, so we can change this as you go. So if you want the dark green to be 0.9 or above, you can change it to be whatever you want to. But so this lets us see at a quick glance, like, hey, up here, this is all good. I don't really need to spend much more time up here. Might if I'm just curious of what's going on, but like I really don't need to. But then over here and down here, it's not as great. So maybe that's where we need to spend more time. And then one thing with interpreting this is, I mean, we don't have observed data everywhere. And we're doing these observed data based on the junctions, and these are showing the results on subbasins. And so what's happening is, let's say, this control point here. So we're taking the statistical results from this control point, and then we'll go upstream to the next control point, where we have more different statistics. And in between these two subbasins right here, they're using the statistics based off of this junction. And so that's how the coloring is going on here. So that lets you see visually overall like how the calibration is going and where you might need to put more effort. If you just want straight numbers, we got this calibration summary table. And so instead of looking at each individual one statistically, we can look at all of our points of interest in one go. So like over here, like this red, we know it's not good. We don't know how bad it is. And over here we can see like, oh, Warm Springs has a national coefficient of -0.4. Nobody's going to say a negative value is anywhere close to satisfactory. So we can see like that is a bad value. But then we can go up here and be like, oh, Nash F cliffs of 1%, bias of 0. Like this is perfect. Like we don't need to spend more time up here. There's nothing more that we can do. So these are just the options that we have for viewing the results and how to see the metrics that we have going on for us. So this is going to end our first video. If you have any questions about our software, need some help, or just looking for additional training, check out these links. They can also be found in the description below. I'd like to thank you all for your time and hope you have a fantastic day.